So once again, welcome to this session. Good afternoon, everyone. So I'm talking about an approach for the qualification and design of connections using post-installed reinforcing bars, which is now implemented in Europe. It is still not there in the US, but I want to explain the background and the explanations, how the whole thing developed. So in Europe, the design of anchorages with post-installed reinforcing bars now is covered by EOTA, or that's the European Organization for Technical Assessment, which is this EOTA, and they have technical reports, and this report called TR69 that covers now the design for the anchorages with post-installed reinforcing bars. And this allows something which is not allowed yet in the US, and this method allows to consider the post-installed bars, which I would probably call as PI sometimes, as better than equivalent to cast-in rebars. So in the US, we can only consider the post-installed rebars maximum as good as cast-in rebars, but in Europe, they are also allowed to be considered better. The design guide covers these applications like column to foundation, wall to foundation, slab to wall, beam to wall, and beam column joints. So this whole concept started, let's say, when I was in Stuttgart in 2013-14, we started talking about it. As Professor Eliasson was mentioning about the harmonization, that was one thing which we wanted to see. And then we said, okay, let's see what happens in the case of post-installed rebar. So, of course, when we talk about cast-in anchorages, we do not consider concrete cone breakout as a possible failure mode. We take the bond splitting of the cast-in rebars, and then we say steel yielding. If your development length is enough, which is beyond this point, you will get steel yielding. And when we talk about bonded anchors, then we do not really consider the same kind of splitting model. It's a different kind of a splitting model. And we say, okay, we have concrete cone breakout, we have steel yielding, and some other failure modes. So he said, why don't we bring all of them together on one chart, which means we consider all possible failure modes, that means including the concrete cone breakout, steel yielding, but we need something new for bond splitting of high performance post-installed bars because they are going to perform better than the bond splitting bars, than the cast-in bars. So this concept also was already investigated long back. One PhD student from Professor Eliasson did this in 2002, and he showed if you have cast-in rebar and post-installed rebar at small cover, both are behaving similar, but if you have large cover, then of course post-installed rebar is giving you higher strength, depending of course on the type of mortar which is used. So in 2014, we performed some numerical studies first, and we showed that, okay, in case of post-installed rebars, if you given your bond strength is quite high, with the increasing cover to diameter ratio and increasing concrete strength, you can actually achieve much higher bond splitting strengths, because for cast-in, it saturates at, let's say, 3 times the diameter as the concrete cover typically, but for post-installed, we could increase the strength quite high. Then we said if we consider also the concept which is given in FIB Model Code 2010, this was available for cast-in reinforcement. They had the model that the bond splitting strength is a function of the concrete strength, the rebar diameter, minimum cover, maximum cover, and the transverse reinforcement. So let's do the similar kind of thing. So the concept which we developed at that time, which is now in the European assessment document, this 332402, we said let's take this approach and try to transfer to the post-installed rebars, which means we need a prefactor, let's call it A. Then we have normalization to the concrete strength, so we need one exponent. This is 0.25 for currently in the FIB code, and we say, okay, let's call it product-specific exponent. And then for the same for the rebar diameter, for the concrete cover, and we have the transverse reinforcement, which should have the similar influence. And then we have also here the influence of bond length, which is accounted for in the FIB model code also, but through a different equation. And then we said, okay, if all of this is there, and this should be less than, of course, the bond strength, because if your cover and concrete strength is quite high, then you will eventually reach the bond strength. So we wanted to develop such kind of a model. And to do that, the first challenge was to develop a test specimen. So we said, okay, we need a test specimen which would allow us to vary the concrete cover, the concrete strength, transverse reinforcement, bar diameter, bond strength. It should have clear bonded and debonded zones. It should allow the measure of the control of the rear end slip, because we also wanted to do it in the seismic or cyclic loading, and unconfined testing. So all kind of things which are going to happen in reality. So we came up with the idea of what we call as the modified beam and specimen, which is now also included in the EAD. So the basic concept of the beam and specimen we took, and then the PhD student at that time, Justus Rex, he developed a nice concept for these kind of specimens, where we have a debonded length in the front, then we have a bonded length, and then again a rear debonded length, and with the recess that would allow the rear end slip control, and so on. So with this specimen, we could easily vary the concrete cover, the transverse reinforcement, the concrete strength, and also the debonded length, and so on. Of course, it was quite some task to develop the methods such that we have clear bonded and debonded length. Justus Rex came up with very nice ideas there. He created like some pilot tube so that through that we can drill it, so to make sure that our drilling is good. And we had the foam tape to seal the gaps. We also, I will not go too much into details, but like we had a polystyrol block to create the recess at the rear end so that we can measure the rear end slip. And we also grinded the rebar at the end, put a tube at the back end so that we have clear bonded and debonded zone. When we did all of these things, we could get a clear, like a pilot hole, the bigger hole to avoid the bonding in this region. We had the clear zone of where we have the full bond and the clear zone where we do not have any bond. All these things are available in the literature, in the paper, so I will not go so much into details, but we took every measure to make sure that we have clear bonded and debonded lengths. And eventually the idea was that no matter where we are, in the front or in the back, in the debonded region, we have at least one plane, weak plane, which allows us to have a free movement without any bond coming into picture. So that way we had clear bond lengths and debonded zones. Further, for the test setup, we said, okay, what happens in reality? So if you have a column to foundation or a beam to column kind of a connection, then if you have a rebar here and it is being pulled, then we have a, let's say, critical crack here, and then we have the bar which is subjected to the bond stresses. So that we took over and converted into like, okay, the equivalent would be the beam and specimen, which is already the concept of the beam and specimen given in ASTM also. However, we consider the transverse reinforcement in a different way compared to how it is used in the beam in the ASTM specimen. That shows the typical test setup. We see the instrumentation. We wanted to measure the crack width, so we anticipate a crack width parallel to the rebar and perpendicular to the rebar. So if there is a crack coming perpendicular to the rebar, then to avoid the concrete cone breakout of the specimen, we had provided the longitudinal reinforcement, which would take up the forces once this crack comes, and eventually it will always fail in the splitting. So here we see some typical test results for the influence of concrete strength. So with these kind of specimen, we always reach the splitting failure of the rebar. And we can see initially the load increases, then we get, let's say, the crack coming from the back, which leads to a rear crack opening and therefore slight drop in the load. But once the crack interferes or intercepts the reinforcement, then the crack is stopped and the load is again taken up by the rebar. Eventually it fails in the concrete splitting. So what we see here, as expected, with increasing concrete strength, even though your bond strength is not increasing, you have higher splitting strength because it's a concrete tension failure mode. The same thing if you increase the concrete cover from 40 to 65 to 90 millimeters we went up to. Again, we got the increase in the effective, let's say, the bond strength or the splitting tensile strength. When we plotted them with as the variables, so what's the bond strength with respect to the concrete cover or concrete strength, we got some trends. And eventually, we came up with an equation very similar to what is given in the FIB model code. We found the parameters, so the coefficient or the exponents for concrete strength, rebar diameter, concrete cover, and so on. And then eventually, we came up with the pre-factor that would give us the best fit. And we can see that in all the cases, we got a very good match then between this equation from the calculated and the tested values. So that was the first step which we took to make sure that we can then compare all the things That means the different failure modes, the bond splitting, the concrete cone breakout, and the steel failure all on one chart for the post-install reinforcing bars. Because we also wanted to see this later on for seismic, so we developed the seismic test protocol. And again, we said this has to be different than from what we do for the anchors, because in case of anchors, the loading protocol is mainly for non-structural applications where we are having a constant crack or the crack cycling is there, but then we have load cycling within a particular range, typically 75% or 50% of the peak load. And we said, no, we want to understand the full behavior throughout the range of interest. So that means not just what happens in the initial range, in the initial loading cycles, but also throughout its load displacement behavior. So we said, let's say if we have a rebar which is failing in brittle failure mode, and the other case it can have a ductile failure mode. So we said, let's define two displacement limits. One is when the load drops down to 80% of the peak load, and the second is 2 times the SU, where SU is the displacement at peak load. And we say take higher of these two, that means higher of either 2 SU or 80% of the post peak. That is our final, like the limit of displacement until where we will do the cycling. So we increase the displacements of the rear end displacement or rear end slip of the rebars with initially 0.1 times SU, then 0.2 times SU, 0.3 times SU, 0.5, 0.75, and so on. And if we do this, then we can calculate, we can get the full load displacement curve. So also, long back, Professor Eligausen gave the testing protocol for reinforcing bars, for cast-in reinforcing bars, where we provide typically 10 cycles at the constant slip, and then we do the residual pullout. So we wanted to compare how our protocol works with the protocol which was given by him for cast-in rebars. So this is an example where we had bond failure. So this was a confined test, bond failure, pull-out specimen. The first case was done with 10 cycles at SU, then 10 cycles at 1.5 SU, 10 cycles at 2 SU, and this was the increasing slip protocol, which we can see is slightly conservative compared to the protocol which is right now used for cast-in rebars, but still is quite decent, especially for pull-out specimen. And when we go to the splitting failure, where we use the beam end specimen and we reach the splitting failure, again we did the same thing at SU, 1.5 SU, 2 SU, and this was with the increasing slip protocol. So what we see is with the increasing slip protocol, we can capture the behavior of the reinforcing bar over the full range of interest, including also the hysteretic behavior, the residual behavior, and all the things. So he said, okay, let's go ahead with this kind of a protocol. Of course, when we want to compare the performance between cast-in and post-installed, we developed some methods where we said, okay, let's do to keep the cost low, let's do the static tests for cast-in rebars, but cyclic tests for post-install rebars, and then we compare the envelopes in a way that our bond strength of post-install should be more than that of cast-in, the energy dissipated by post-install should be more than the energy dissipated by cast-in, and also the residual capacity should be more than 40% of the residual of the peak load of the cast-in. So that way we first developed the bond splitting model, and then we wanted to see how we can apply that to the structural connection. So this is a part of the PhD of my student Vinay Mahadik, who worked on the column to foundation connections, where the column was connected to the foundation with different embedment depths, and as a cast-in hooked bars, cast-in straight bars, as well as with the post-installed straight bars. Some typical results I will show you here. This one should have started first, but okay. So the result on the left side, that is having, I think, let me see, I cannot see it so well from here. Yeah, this is the cast-in CIS, that is cast-in straight, and this is post-installed with everything else the same. So the embedment depth was 350 millimeters in both the cases, and we will see that in case of post-install, we are able to develop the hinge in the column, whereas in case of cast-in, it comes out in a pull-out kind of behavior. We will also see that in the hysteretic loops, that after reaching peak, there now we start to get large pinching, typical of bond pull-out failure, and we have large strength degradation, whereas in case of post-installed, we are able to develop the hysteretic loops, fully formed hysteretic loops, which is due to the steel yielding. We also did similar test on beam column joints. So once again, this, I think, let me see once again. Yeah, this is for cast-in, and this one is for post-installed. And once again, we see that, okay, in case of beam column joint, eventually it was failing by joint shear failure in both the cases, but the performance of the post-installed one was quite similar to the cast-in with hook. So in the cast-in case, we had one side the hook was bent in, and the other side the bar was straight. And that's why we see this unsymmetry in the results, but in post-installed, of course, we have post-installed on both sides. We see symmetric results, but the failure load is much higher than what we got in case of cast-in straight bars. Also did some tests with wall foundation connections. Sorry for this, I do not know why it's happening, but we can see the concrete cone breakout happening in case of wall foundation connections. We varied the thickness of the wall and so on. So if I now show you the comparison, again given in the thesis by Vinay Mahadik, of what would be the failure load predicted by the current Eurocode approach at mean level. So the failure load predicted would be rather small here, and we would always assume a pull-out failure because we consider it as an equivalent cast-in bar, but the actual failure loads were much higher. So in case of the Eurocode, so this column foundation joints, the Eurocode formulations, they were predicting significantly lower values compared to what we got in the tests. And when we use the new approach, which is now in the EOTA TR69, then we are able to predict the failure loads and the failure modes rather accurately. So that was the kind of background and the whole story, how it developed. We wanted to plot everything on one plot. For that, we needed the bond splitting model. That's why we developed the beam end specimen. We developed the cyclic loading protocol, and eventually we checked it on the structural connections, which is now all approved in Europe. And hopefully we can adopt a similar approach in the US in maybe a decade or less, hopefully. Right? Thank you very much. And if you have questions, I'll be happy to answer.